Welcome to All Space Considered, everybody. It is the first Friday in June, and I'm Dr. David Reitzel. And with me tonight, as always, is Patrick So, and of course, Chris Butler. And we've got a wonderful show for you tonight. We're super happy about it, and you can see our topics here. We've got cosmic news stories, and we've got some star formation. We've got the solar flares caught by a new instrument. We've got some shrinking planets could solve a mystery. Some information about Barnard's star, and that one's been going on for quite a while. We've got the total lunar eclipse coverage, of course. We had a beautiful total lunar eclipse. You can see the picture in the background here. And then we're going to do another inquiries from the foundation, out to launch, our sky report, and then we've got our second half of the show with some pretty pictures and solar system weather with Katie. And she's also going to talk about a swarm of sprites, whatever those happen to be. And we're going to talk about some heavy metal comets, do a Mars update. And then we are super, super excited because we have Dr. Paul Byrne here to talk to us about the 2 missions that NASA chose to send to Venus. So we're going to hear all about it. He's an associate professor of planetary science at North Carolina State University. He runs a planetary science group at North Carolina State. He's super active on Twitter and is a big proponent of going to Venus. In fact, he's currently working on something called the Decadal Survey and is on the Venus panel. He can't tell us any of the secrets that they're talking about, but he can tell us about why that's important and what work's being done on that and how these missions fit into that. So it's a super exciting guest to have just a couple of days after NASA announced these missions. So first of all, though, I do want to announce our show is made possible by Griffith Observatory, the City of Los Angeles, the Department of Recreation and Parks, and of course, the Griffith Observatory Foundation makes much of what we do possible by the donations of the members. So we very much appreciate that. A lot of our equipment is purchased with those donations. So on with tonight's show. First of all, I'm going to tell you a little bit about some star formation. This is, of course, that beautiful Eagle Nebula that everybody's familiar with. The Pillars of Creation, some people called it. And on the left-hand side, you can see sort of a typical color image of it and that dark dust and gas that you can't see through. And the pillars are being eroded away by bright, young, hot stars that are kind of eroding that gas and dust away. Now, if you look in the infrared, however, I don't need to click because it's already up there on the right-hand side of the image. You can see it there. The infrared's the right-hand side. You can peer through that gas and dust, and you can see the stars. Now, a lot of stars are being formed there. This is a region of active star formation. So we want to understand that star formation, and that's what that video you saw to open tonight's program was all about. You have hot young stars in the middle, you have hydrogen, you have H2 regions, which is ionized hydrogen gas, where the electrons have been stripped off, and it's this interaction with the magnetic field that make this so interesting. Now, this diagram I had to put in, I know it's a little janky, but this was from Mike Bolte. He was one of my professors at Santa Cruz, and I love that my staff found this for me. I didn't pick it, but I kept it because Mike Bolte was one of my professors at Santa Cruz, and terrific guy too, wonderful astronomer. Anyway, this is the basics of what went on, and these quick drawings, by the way, were done by our very own Chris Butler, so we can thank him for Griffith Observatory Originals. You start with a big molecular cloud, mostly hydrogen and helium, and you start stars somehow collapse. That collapse gets started off and you make these young stars. Well, the energy from them can create a shock wave, and we thought it would trigger more stars, where that little arrow forming more stars in that shock region. Well, the stars that formed will kind of drift away, form an open cluster, drift away from that molecular cloud in the background, and then eventually form an older open cluster. The question is, when we do a simulation, do we get the right ratio of stars? Do we get enough big ones to small ones, enough medium-sized ones? We weren't getting that right. It was difficult to make the right kinds of stars in those simulations. So that one you were watching was called Starforge, and they decided they were going to add in magnetism, they were going to add in jets. Those jets you saw coming off the stars were all simulated, and they had to use a supercomputer, of course, to be able to get this done. Lots and lots of hours on the supercomputer, and it made a simulation, of course, that looks something like this. Now, do I need to click on this to make it? Oh, there it goes. Perfect. And you can see the gas starts to get pulled together. The magnetism within there drives the direction it moves. Star formation gets triggered. Energy starts to get piled into this gas and dust. And those jets start to shut down the star formation. They notice that the jets can actually quench the star formation and make it kind of shut down. There they go. They're those jets that I was talking about. They'll shut down that star formation and turn it off. So we get a zoom in here on the jets, and they're able to simulate these in these supercomputers. So zooming in here, one more forward. Sometimes I get impatient. It's going to click on me. You can see there, looking at the one, the very, very largest sizes there. That's their whole simulation. You can zoom in on a smaller pocket and then continue to zoom in until eventually you're in the upper right, that sort of S shape that's up there. That's the jets coming off of that. And those jets do shut down the star formation, but they still had a problem. They were making stars that were too massive. The biggest stars we see are around 100 solar masses or so these days. Something about their simulation wasn't doing that quite right. Now, maybe we can get informed by reality. This is a real star cluster. This is a cloud of gas, a molecular cloud, a giant molecular cloud forming stars. Some astronomers said, well, let's study it and let's study the magnetic fields there. In fact, this is kind of a joke, to me at least, and to a lot of astronomers. For the longest time, you'd go to meetings and people would say, well, we're having difficulty simulating the gas movements within the galaxy. We're having difficulty simulating the star formation. And someone, you know, okay, I won't call them the name that people would call them, but eventually someone would raise their hands and say, have you considered magnetic fields? And people would say, of course I haven't considered magnetic fields. They're too hard. Well, they're no longer too hard, and people are doing this within their simulations. So it's pretty exciting that this is going on. Now, these folks aren't simulating it. They're measuring what the magnetic fields are actually doing around these complexes. So these little dashed regions, those are where they're finding stars that have formed. The gas is there. The dust is there. Well, you can use something called a polarimeter to measure the polarization. Polarization is like your fishing glasses or your sunglasses for driving. They have some of them have polarized filters in them, and if you turn them, you'll notice the brightness of reflected objects will change. Well, they do the same thing here. They turn the polarizer and take many, many different pictures at different angles, and they can see where that light is getting reflected and how the magnetic field affects it. And here it is. The yellow lines, the length of them is the strength of the magnetic field. The direction of the line is the direction of the magnetic field. So you can see how, let me get my little pointer out here, little laser pointer. You can see how the magnetic field lines kind of ring around the bigger feature. You can see here they're around that direction. They kind of make a loop. Down this direction, they're primarily across. So there is structure to these. This star formation that's going on there is affecting things and giving a structure. And the dense clumps are very magnetic there. You can see down below, the purple area has strong magnetic fields. So the magnetic fields are doing something to the star formation. And it turns out they quench it. They actually are able to kind of hold the gas in place and prevent that shock that we thought should be making more stars from creating those stars. I should turn off the laser pointer. My mouse fell off my lap here, though. That's why we have a laser pointer floating around randomly. So anyway, these magnetic fields shut down the star formation, and it's interesting. So maybe that first simulation should have the magnetic fields hold the gas in place a little bit more, and maybe they'll get the right numbers. Who knows? Now, if this sort of stuff, if you like it, you should check out a book on by NASA that came out. It's an ebook. It's a free ebook called The Lives of Stars, and you can download it straight from NASA. Our moderators in the chat hopefully have a link to put it in there. They'll put it in the chat down there and you can find it. But there's all sorts of interesting information, everything from gravitational wave sources and all the stars that we see within clusters and things. So free book from NASA if you like star formation. And there's the link there if you want to copy it down by hand on the YouTube page. So enjoy. So Patrick, you have an interesting story here about some measurements that were made recently. What's going on with these?
Yeah, so this image here is actually an artist's conception of the solar orbiter. It's a European Space Agency mission with a lot of collaboration with NASA. And you may have heard, we've done stories on this, of the Parker Solar Probe that is sent very close to the sun to study the sun's corona. Well, this spacecraft is a complement to that because it will actually go as close as the, actually just kind of closer than the orbit of Mercury, about 26 million miles, and experience a temperature of 900 degrees Fahrenheit. But it's loaded with instruments, and we're going to go ahead and go to the next slide here and just show you its typical orbit. Here is just close to the planet Mercury. This spacecraft has a lot of instruments, and we're going to feature 3 of them because they were very instrumental to actually observing a coronal mass ejection, which is an enormous eruption from the sun. So one of the first instruments is this one, which is called the Extreme Ultraviolet Imager. And this basically captures layers of the atmosphere just above the visible surface of the sun, or what we call the photosphere. And you get an image kind of like that. It looks very pretty, but it's in ultraviolet light. Now, the next image, or rather the next instrument, captures the corona, the outer atmosphere of the sun, just above the coronosphere. And this is a little bit further out. This is roughly a view, that kind of reddish part there that you see in the image surrounding the ultraviolet image. It's a coronagraph, so the sun's visible portion is blocked out by a occulting disk, and we see the faint outer corona of the sun in visible light and also in ultraviolet light. And then the third instrument is this one, which is the visible light, which actually observes visible light further away from the sun. And this one is observing the corona of the sun from 2 to about 18 million miles away from the surface of the sun. So putting all these 3 instruments together on February 12th of 2021 this year, all these instruments simultaneously observed a eruption from the sun, and we'll go ahead and look at this movie here, combining all 3 instruments. And within that red circle, you see a tiny puff of energy, actually material that's released from the sun. And the next instrument, which is the METRIS coronagraph, you can see the material moving further out, and finally, much further out, up to about 18 million miles in this 40-degree view of the sun. You can see the material ejected out from the coronal mass ejection, which are particles basically that make up the solar wind, but are traveling about 1 million miles per hour from the sun and out into space. This is a close-up image of it, so we can see how that material is moving from the sun. Now, this diagram actually is a kind of like a simulation. So it looks kind of like a spirally thing on the left there. That shows the sun, which is that white dot in the middle. The red diamond shape is where the solar orbiter was. And then if you look at the 1 and 2 o'clock position, you see the material ejected away from the sun in that large coronal mass ejection. So this is a very interesting observation, and it's one of the early observations from the spacecraft, which was just launched last year. Some of the instruments are still being calibrated, and in the next few years, we'll get some really detailed images of the sun from these instruments and other instruments on board the solar orbiter. This will obviously provide us with more details on the activity of the sun, and also the coronal mass ejection, which is the mechanism which is kind of not well known at this time. So more images to come and more data and discoveries from this spacecraft.
Well, very neat stuff, Patrick. Thank you for sharing that. And, you know, coronal mass ejections, those are the sorts of things people kind of fear when they head towards planets. They can cause destruction, they can cause mayhem if they're really large. Satellites need to take cover. And it's these sorts of events that actually can affect planetary atmospheres or exoplanet atmospheres. Here's an artist's rendering, a pretty well done one actually, of sort of the core of a bigger planet that got stripped away. All the atmosphere got stripped, leaving behind probably a rocky metallic core. You can see it's hot probably, it's very close to its star. So, you know, a very, I don't know, a place you wouldn't want to hang out at. And maybe it's that sun, that star off in the distance that was sending those blasts off and clearing it. And in fact, we think that sort of action is indeed responsible for something that we call a gap in the distribution of exoplanets. When you look at exoplanets and you bin them, so you take the relative size, and down below is the size relative to Earth, so Earth would be here at a 1, and then the number of planets, the exoplanets really, per 100 stars that we think are out there, and this is based upon measurements. You get a diagram that looks like this. Now this first little gap here might be real, might not be, could be the way it's been, but it's this second gap that the laser pointer's in between here. That's real. That doesn't go away no matter what we do. In fact, the more data that are taken, the bigger and the more distinct that gap has become. And it's between something we call super Earths. Kepler, what is that, 452b, is 2.5, 3 times the size of Earth. It's bigger than Earth. It's larger, more massive. But then Kepler 22b is a little bit like a mini Neptune. So why is there a gap between? Why isn't that a smooth distribution between those? What in nature is making that happen? Well, what we think is happening is indeed the sunlight is making the planets change. So you have a gap, and as the planets, as the gas envelope gets eroded off that core, the planet actually moves from being a mini Neptune, will, what they say, jump the gap and become a super Earth. Now, what is the evidence for this? You might say there's no evidence. This is craziness. Well, people dug into the data. We now have enough exoplanets, we can start to group them together. The Kepler telescope, TESS is now giving us even more. We look at the data, we bin it. And it turns out the planet radius, again, is down below. Earth is a 1 size. Planet density, ignore that for right now. We don't need to worry about it too much. What you need to see is that pink region. And then how it moves, that green dash I'll put around it, with age. It's located in the pink spot when they're young. When they're older, it moves to the right and gets larger. All right, so what's going on there? What's going on there? What's happening is indeed the planets are shrinking with age. The star is blasting that planet's atmosphere, and the planet actually changes size. So the very young ones, you have more of these mini Neptunes and smaller super Earths. The older ones, the smallest of the Neptunes, got transformed into a large super Earth. So the gap actually moves, and they're seeing that gap change position with time. So in a very, very young cluster, the gap is actually in a smaller position. In an older cluster, the gap has moved different. Well, I don't know if they're doing it in clusters, but they have to age date the stars. So really what's happening is the planets are being transformed with time. So this is kind of complicated. With exoplanets are changing what they look like over time, it's super interesting to study, but it becomes hard to understand. Also, the core of the exoplanet itself can affect the gas loss rate, the mass that's there, the gravity that's there, and of course, how bright the star is. The star might cause variability in the rate the gas is lost. So yeah, Neptune, in the right system, at least not in our solar system, could be transformed into, well, a super Earth, certainly not an Earth. So very, very interesting stuff. But it's not quite completely making the exoplanets go away. Chris, you've got a story about an exoplanet that seems to come and go
Yes.
like almost like clockwork. So
Yes,
what is
yes.
the latest on Barnard star?
Oh my, yeah, folks, so you all understand what in the world it is that a space artist does. Scientific data is the real gold standard, scientific data acquired by researchers. But sometimes what it'll get you is, well, like you were just seeing there, a diagram, something like that. But the public, you and me, being curious folks, we clamor to see what something would be like. So artists will interpret and imagine. We already saw another nice piece of art there. And that's what I do. We've had something happen here that's a good case in point for you folks who may be consumers of astronomical art, and also for folks like me who do that. Something that's important to remember: we're a data-driven, hobby and profession, and well, sometimes we do get a little bit ahead of ourselves. And I have a classic example of that, something from my life over many years. This scene here, if I can, I'll play that.
Yeah, I left the laser pointer on you.
That's okay. Let's see, does it play? No, it does not play. All right. The scene you're looking at there is something that I did actually a number of years ago, of a planet around a star called Barnard star, a frozen icy surface with a thick atmosphere and this distant orange sun hanging in this spooky, mysterious sky over the ice. This is a world I've seen. This is a world I believed in. I'd invested in it artistically. And for somebody in the average public looking at this, you'd look at a scene like this and say, well, I know all about it. I've seen it, right? A picture's worth 1,000 words, and sometimes it shouldn't be. In this particular case, I would have to revise this drawing dramatically because of some new discoveries that have just been made. Let's start out with Barnard star just for a moment. It's a famous star. The gentleman in the picture, Dr. Emerson Barnard, is the man it's named for. It was famous not because it's bright. The picture you're seeing is a zoomed in telescopic photograph. As a matter of fact, it's a very faint star. You can't see it with the unaided eye at all. He proved in 1916 that this star was actually very, very close to us. It was a surprise, a discovery of a new star close to us. So it was well known. If you look at diagrams today, you'll see that with the sun there in the center, those are not orbits of planets. Those are rings of distance. You have, at just about 4 light years, you've got the bright yellow dot there of Alpha Centauri. Right next to it is the other closest star, Proxima Centauri. That's your red dot. Those remain the closest star systems we know of to our own, like 4.2, 4.3 light years away. But Barnard's star, marked with the red arrow on the other side, is at 6 light years. So this was a surprising thing to find one so close, and it remains the second closest star system to our own. People have always wondered if it had planets. And guess what? The announcement came in the year before I was born, 1963, that Dr. Peter van de Kamp, a Dutch astronomer working in the United States, had painstakingly watched Barnard star and detected that it was wobbling slightly. Now, what would do this? The gravity of a planet going around it could displace the star slightly. Now, we use those techniques a lot today, but I want to be clear with this. This is the old school way of doing it, called astrometry, which means star measuring. And he's literally looking at photographs of the star through a telescope. And of course, it's not a tiny, tiny little pinpoint. They make it as small as they can, but it's just kind of a blob. He's looking to see a tiny wobble around the edges. Very, very hard to do. But he thought he found a wobble. And he announced that he had found a planet around another star, a planet about the size of, say, Saturn, something like that. Now, the thing that's interesting about this, there had been no announcements, no formal announcements of somebody saying they'd found a world around another star. In 1963, we didn't know of any. This was an example where somebody said, yeah, I got it. And it's around Barnard star, that famous star right down the freeway 6 light years away. Everyone was really excited about this, but there was a problem. Other scientists looking for this, well, here's a scholarly paper. This is 1973, and skepticism was building. People could not find the wobble. So those worlds that, well, you asked me as a kid back then, I would have known all about those planets. I could have told you all about them. And now it looked like they might not be there. That's a little disappointing, but that isn't what science is about, is the question of fulfilling your wishes. The question was what's really there, right? And it looked like they weren't there. So all of us who were early adopters of the Van de Kamp planets, we had to let them go. Okay, so those giant planets, whatever they were, they just weren't there. So, okay, fair enough. Time goes on. Barnard star has no planets. And then in 2018, suddenly, big news. Headlines, lots of headlines. I quoted the headlines here for you folks so you can get an idea of the pent-up frustration and excitement people were feeling about this. At last, a planet for Barnard star. People have been staring at it, testing, trying to find something. Look at the second headline. Barnard star, the great white whale of planet hunting. All right. This is one we were waiting for. People ran off ahead of themselves asking, though, it looked like it would be very, very cold, but somebody's even speculating that maybe it could be a home for life. The fact is, people got excited about this. This was not a big giant planet like Jupiter or Saturn. This was, well, like we were just talking about, a super Earth, a slightly larger than Earth planet. It was in a place where it would be very, very cold, but it might have a solid surface. Here's an example of an artist's rendering. This is from the European Southern Observatory, not one of mine. And here, we're just letting our imagination go to town because we didn't know very much. And I want to make the point for the astronomers who reported this. They were cautious. They said, look, this signal is barely there. This is right on the edge of what we can do. Other people need to look at this. Well, other people did. That's what science does. So they looked at it and, oh boy, guess what? Other astronomers looking at the signal very close. Yeah, the data is there, but the problem is they failed to account for something. It has to do with the star's rotation. It was something the original discoverers knew could potentially be a problem, but it turns out the planet just doesn't seem to be there. So what does all this mean? What does it mean for you guys? Well, I mean, I'm allowed to feel a little bit like Charlie Brown with the football when Lucy pulls the football back. I mean, in 1973, I thought I had a planet, and it turns out it's not there. And in 2018, I jumped up and down. I said, that's good. I like that planet. It turns out it may not be there. Notice, by the way, it's the scientists, the astronomers, who are checking each other's work. And if there's a problem with it, they say so. And that's okay. For guys like me, well, you know, initially there was nothing. We didn't know if there was anything around Barnard's star. Today, then we had the 1973 planets. Whatever it was, they might have been those big gas planets. Maybe they had rings. Maybe they had moons. All of these ideas that I got so excited about. But the data in the end showed probably not there. So we had to revise our ideas, the astronomers and also the artists. So in 2018, not those giant planets, a smaller planet, more like the Earth, with perhaps an icy surface under a relatively thick atmosphere, maybe possibility of water under an icy crust. And we all got kind of, you know, excited about that possibility. And it's true for all the exoplanet discoveries. All of them have to be checked. Some of them are more definite than others. This was always on the edge. I'm glad that we found out that this world that I imagined isn't there, because this means we are hunting. We're going to find the data. We'll find out what is there. And it's going to be exciting for all of us, not just the general public and not just for the astronomers, but also for artists. Anyway, that's what I wanted to share with you folks today. And we will see what happens with Barnard's star.
Yeah, well, thank you, Chris. Like you said, you can't get upset. Well, some folks can, I see, and would understand, but science and the data are doing what they do. This is how we can trust science will eventually come on the right answer. Our answers get better and better as we improve what we believe in based upon our observations. That's what we do. And at Griffith Observatory, we make observations. And one of the observations we made recently for folks is we streamed the eclipse that we showed off. And Patrick, you've got a story to tell us and some images from that night, that beautiful night that we were up all night long from the roof of Griffith Observatory. And we brought people that eclipse. If you haven't seen it yet, you can go to the channel you're watching this on, the YouTube channel, and see either the short one or the long one. But Patrick, what did we do that night? What was it all about?
Okay, well, this is more of a recap of the total lunar eclipse that occurred on the West Coast and also in Australia as well. But it occurred last week, so last Wednesday. And it was the first total lunar eclipse of the decade. So we were really excited, and we did indeed stream it, and we set up equipment. I just wanted to start off with a kind of like a behind the scenes view of what we did in preparation for the eclipse. We had to do, first of all, a sight line to see if the eclipse was visible from our 12-inch telescope on the roof. Unfortunately, as you can see from these sight lines, the red arrows means that it was not visible from the telescope dome, mainly because the planetarium dome hid the moon. The numbers that you see there, you can see the time 1:48, and then in parenthesis, the first number is the azimuth, which is the bearing of the moon on the horizon, and the second number, 33 degrees, is how high it was. It was visible in the beginning stages of the eclipse, but for most of it, it was blocked. So what we had to do was find an alternative site and set up a portable telescope where that green X is. We see that, you can see it right there, streaming and scope and streaming station. Okay, so we did exactly that, and on the left there, that's the telescope we used. It's a Celestron C11 HD on a very expensive mount, and and on the right there is Blake Estes, who's our telescope demonstrator, and I just want to give a shout out for him, because he was the one that guided this telescope on the moon throughout the night, and this was his last task here at Griffith Observatory. He is going to be leaving for Australia and gone forever from us in about 2 weeks from now. But anyway, it's great to have him and to have him participate in our event. We had our streaming equipment set up by Matthew Delando, our production engineer. You can see it's all lit up there with various views of the eclipse and different video feeds that we sent out to the stream. And here we all are on the roof, all prepared to stream the total lunar eclipse. Now we're all prepared, and you can do all these plannings to the minute, but what you can't plan for are clouds. And we did have some partly cloudy skies throughout the evening, which did obscure the view of the moon. But nevertheless, when there were gaps in the clouds, we got these very beautiful images of the lunar eclipse. Here it is. These pictures were taken by Anthony Perkic. As the shadow of the moon, the umbra, that dark part, begins to sweep across the lunar surface. And you can see it gets a little bit redder here. And this is almost to totality. The redness, of course, comes from the light filtered by the Earth's atmosphere, coming from all the sunrises and sunsets around the Earth. So we'll go to the next one. This happened. So what happened at 4:11, which was the beginning of totality, we got some clouds and we weren't able to see the totality, which happened at 4:19 a.m. Pacific Daylight Time. But we did get this picture right after totality finished, but nevertheless, it was just a beautiful sight. The moon was indeed a beautiful red-orange in appearance, which gives you an idea of how transparent the atmosphere is at the time of the lunar eclipse. The clouds did make it look beautiful, and you can see a bit on the lower left, right there. And then it got a little cloudy again, and then it got a little bit brighter again. Here's a view from the roof as we look out towards the southwest of the lunar eclipse. And we basically watched through to dawn. Here is the blue hour, and finally sunrise. We were all excited to see it. There were people that did come up to see it. They were hiking, and it was a good event all around. At least we got to get a glimpse of the eclipse. Now, if you've missed this one, the next one, I should show you this because this is the 1 minute time lapse of over 3 hours of observation from that telescope. And the moments where you can't see the moon, of course, it's cloudy.
Well, there we go.
And then we had a period of clouds, and then it got clear again. And just enough time to miss the totality, mid-totality, but to see the ending of a few minutes after totality. All right, so that was what we got. And here is our next eclipse. And believe it or not, it's occurs on November 18th, 19th in our time zone. And this is not a total lunar eclipse. This is going to be a partial eclipse, although this is one of the deepest partial eclipses that we're going to see, where the moon is almost entirely within the Earth's umbra, the darkest part of the Earth's shadow, which causes it to turn red. And there is a little snippet of the moon in the southern part that's just outside the shadow. So this is going to be a very interesting eclipse to look at. And we are actually in the area of visibility. So the entire eclipse will be visible to all of us. So we're hoping to stream that just before midnight and through to the early hours of the morning. So mark your calendars for this event.
Yeah, thank you, Patrick. Looking forward to hosting that next eclipse. We'll have a lot of fun with it, even though it won't be a total lunar eclipse. It'll still be a lot of fun. So we've reached the part tonight where we get to take a question from our foundation, our inquiries from the foundation section. Every month, our foundation solicits its members for a question to ask us here at Griffith Observatory. And tonight, we're happy to have a question from Byron Hayes, and he wanted to know, what are the observations closest to the Big Bang that have been made? Great question. So the Big Bang, of course, is the beginning of the universe. We think about 13.8 billion years ago, filled with energy. Some of that energy gets turned into particles back and forth. Eventually, the particles separate from that energy. However, what can we actually see? What can we look back on? Well, the furthest galaxy light, so sort of starlight that we've seen, is from a source called GN-Z11. And indeed, it has a redshift, or Z, of 11.09, which is ridiculously big. The light traveled 13.4 billion years to get to us. So when the light left us, the universe was only about 400 million years old, if these numbers are correct for this galaxy. The proper distance, meaning how far is it right now, it's 32 billion light years away, because the universe has expanded in that time. It took the light to get to us. So the thing is a lot further away now than it was when it left. And the constellation it's in is in Ursa Major. Now you can see the data that were responsible for this. Now, a little bit confusing, but hang with me. I'm not going to spend too long on it. But you can see here the data is the red. It has a sharp incline and then sort of smooth with little dips in it. Well, this over here is the bluest light that is going to get created. It's sort of a drop off there in the starlight. So we can look for that in models. So they go in and fit this, and that's how they get the redshift. Could it be wrong? Sure, it could be wrong. This is the best guess they have to find it. It's very difficult to do these sorts of observations. And this is the reason we're excited to get things like the Europeans' extremely large telescope, TMT, wherever it eventually does get built, whether it's on Mauna Kea or moved off to another site. That's a discussion for another time, folks. And also, of course, the James Webb Space Telescope will give us observations from space that'll be able to see a lot of these objects. Now, this isn't the furthest thing we've seen or the thing that is closest. Really, the thing that is closest to the Big Bang we've seen is really the cosmic microwave background radiation. That is a real surface. That's when the universe was opaque. It's sort of in every direction. It was glowing nearly as brightly as the sun, and it was opaque like the sun. So if you want to see that surface, that's what you can look back to and actually hit it. It's only about 379,000 years after the Big Bang. So it's a little bit further back. It's a little bit closer. So that's our main questions from the foundation. We had another great question from Brian Ferguson, who wanted to know, we can approach the speed of light, but Einstein's equations and our measurements and every bit of physics we've ever done says you can't go faster than it. That things happen, special relativity, general relativity kicks in. You can't get past it. It's a physical limitation. He wants to know, or what concepts to get past it. What can we do about that? Well, you can't go faster than the speed of light. That's just impossible. But what you can do, you can mess around with a distance. You can do things like fold space. You can tunnel through space. You can warp it and make the distance shorter or find a way around. So we cannot travel through our own space faster than light, but maybe you could go outside of it. So great question, but you weren't the main question this time. If you have other questions, or Brian, if you have a different question, you want it to be the main one, submit them for next month. The foundation also has a very special opportunity. We're really exciting. They have a special announcement coming from them. Plans to reopen the observatory are in progress right now. So that's brand new news. I don't think anybody's told anyone this yet. We don't have a date to announce, but it's going to be coming soon. And the foundation is going to host a special night just for members. So this is your chance to join the foundation and go see Griffith Observatory before we reopen to the public. And this is going to happen on, this is our first on-site event since February 2020. And we're excited to have members come back, take a look at some of the changes, take a look at the, all the exhibits. It's going to be a lot of fun. The Samuel Ocean Planetarium will be open. The Leonard Nimoy Event Horizon Theater will be open. Opportunities to look through telescopes. So, it's time to join or renew your membership, and then you can come visit the observatory on June 18th. It's super, super exciting. And, we haven't been closed for 15 months like this in a long time. It was unexpected, unprecedented. So with contributions from the foundation, we were able to create an online presence. We were able to do some new things. So thank you to the foundation. This is an opportunity to thank them. And soon enough, the rest of you will be able to come join us too. So now it's time to turn towards the launches that have been happening. So Chris, you've been paying attention to launches and things. What's been out to launch lately?
Well, gosh, yeah, quick update on the world of launches, because actually they're going on at the rate where there was a launch yesterday. There's an event tomorrow. We're absolutely in the midst of all these things. Let's jump around real quick and get a look at what's going on. First of all, I mentioned something launched yesterday. That's a cargo resupply mission from Cape Canaveral. This is a U.S. mission using the Cargo Dragon. Now, the Dragon spacecraft of SpaceX can carry people. They also have a cargo version. That's what this is. No people aboard, just cargo. They launched yesterday. They are on their way to the space station, and they'll dock with it tomorrow. The other picture that you see here shows a solar array. This is a roll-out solar array, they call it, or ROSA for short. This is a new design of a solar array to give electric power from sunlight for the space station. They're lighter and they're more powerful than the ones we'd been using before. They had one previously at the station. They tested it. This one is going to actually stay at the space station and be one of several. There'll be 2 more of these solar wings that will be delivered to the ISS a little later in the year. That's going on right now. Something else that's going on right now, the Chinese are building their own space station up there, the Tiangong space station. They launched their first module for it. You may remember we talked about it last month. The Tianhe core module is up in orbit. They're going to be sending taikonauts, which is what they call their space voyagers, up to it. But before they do, they are launching some supplies. They've launched the supplies. They've docked with the Tianhe module, so they'll be available there for the taikonauts to use during their stay. The Tianzhu, as it's known, means heavenly boat in Chinese, is a very capable vehicle. It actually can deliver about twice as much cargo as our own Cargo Dragon. However, one thing Cargo Dragon can do that this one isn't designed to do is bring cargo back. It can't land because these vehicles don't have to have parachutes and heat shields and landing systems, all that. That means they can carry more up, but they can't bring any down. And Cargo Dragon will be doing that when it finishes its mission. Just a little different design of vehicle. The Russians, they also have a very capable cargo craft, the Progress. The Progress mission is going to be at the end of the month. June 29th is planned. Yeah, and it's going to launch up to the International Space Station and dock there and deliver supplies. Now, there are lots of things to talk about with the International Space Station. Russia is evaluating what their role is going to be with it going forward. There's an older module that the Russians have attached to the ISS that they're going to be decommissioning and actually casting off the station. They have some new modules coming up as well, but we'll see what the long-term plan for the Russians is, or maybe they're just going to, like the Chinese, make their own space station that'll just be theirs. We'll see. We last month talked a lot about Starship serial number 15. Nobody on it, just testing this gigantic monster rocket. This is the one that was able to fly up to airliner height, turn around, fall back to the ground, and land safely. The first time that this design has been able to do that, it's a big achievement. We were thinking they might launch it again, but they changed their mind. They rolled it back. And it looks like they're going straight to Starship serial number 20. 20 will not just be this. This is just the upper stage. Starship number 20 will be riding on top of the first stage, a test of both, and a test going all the way, not to airliner height, but to orbit. And SpaceX has revealed their plans, their proposal. The mission would, if you look in the upper, you can see actually both stages lifting off there in that artist's concept. But then if you look at the picture to the right of that at the top, you see a little squiggly line. That's the path for the first stage. The first stage cannot make it all the way into orbit. They have to dispose of that stage. Now, the plan normally would be to land it, but they're not ready for that yet. They just want to get the launch, and they're going to drop it into the ocean, and that shows where, just off the coast of Texas. The image at the bottom shows a launch from Texas takes you and the upper stage on its way to orbit across some pretty interesting territory. There are a lot of islands down there with a lot of people, a lot of population. When you launch from Cape Canaveral in Florida, there's nothing but ocean to the east. It's one of the reasons we don't launch east-west orbits from California. Launching east from California, you're going to fly over Arizona and places like that. So they have designed this flight path to thread between Cuba and the Bahamas and all the rest of this. They're going to send the second stage up, put it into orbit. They're going to bring it back through the atmosphere, test the heat shield, and then they're going to land it in the water, a splashdown. It's not a proper landing for it, but they're going to land it somewhere off the island of Kauai in the Hawaiian Islands. That's the plan. It's been proposed. We'll see what happens. Maybe August, September, who knows? But they're working on it now. It's pretty exciting. As far as upcoming launches, just a heads up, in July, we're looking at a date to be determined, secret military launch of the Falcon Heavy. That's the 3 rocket core stage version of the Falcon rocket. The big one is going to launch a mission for the Air Force. Don't know the date right now. Or actually, yeah, it's a Space Force launch, in fact. At the end of the month, we may have a flight of the Boeing Starliner spacecraft designed to carry people. It had trouble on its first mission to the International Space Station, didn't get to the station. They have decided to go ahead and do a repeat flight. May happen at the end of the month. So that is my world of space updates. Thank you.
Well, thank you, Chris, for that. Appreciate that. Always exciting when SpaceX is launching bigger and bigger stuff. I think somebody there in Texas just wants a vacation to Hawaii myself.
It'd be a pretty quick trip.
Would be. So, Patrick, what's been up in the sky, and what should we be taking a look at in June?
Yeah, so there is a lot of interesting things to look at for all of us who stargaze in the sky, particularly in this month. And we're going to start with an evening planet, planet Venus, the brightest planet in the night sky, which is kind of low over the western horizon right after sunset. We're going to be hearing a little bit more about this planet, second planet from the sun, but it is now visible, and you can even go out now and take a peek at the outside, and you might get a glimpse of it. But it will be climbing a little bit higher in the sky. Now, just to look forward to the next time, on June 11th, the one-day-old moon will be right next to Venus. So you can see both Venus and this very thin crescent moon just above the western horizon. So that's going to be a very interesting sight. If you're at Griffith Park, it will be to the left of the Hollywood sign, both the moon and Venus. Now, just a few days later, the moon will ascend in its above the horizon and move along in its orbit around the Earth, and will be just about 3.5 degrees above the planet Mars, which is a lot fainter than Venus, but nevertheless, if you find the moon, you can find Mars right below it in the dust light. Okay, moving ahead. For our evening sky in general, if you look to the south, there are a few bright first magnitude stars that you can look for. One is over in the south, Spica, which is located about 40 degrees above the southern horizon in the constellation of Virgo the Maiden. Down towards the southeast is a reddish star known as Antares in the constellation of Scorpius the Scorpion. And we have a telescopic picture of this star in our next slide. This is taken by Anthony Perkic, and this is the star Antares. Its color is a little exaggerated, but you can see the intense redness of this star, which is basically a giant it's a supergiant star, and it's in its kind of late stages of its life, located about 500. Yeah, go ahead, David.
Well, I was just going to say, are we seeing the surface of the star there, Patrick? What are we seeing there? That's very exciting.
We're just basically we're seeing the light from the star, and we're not really seeing much of the surface there, of course. But it just looks brilliant when it's magnified.
Too far away for that, and we're seeing effects from the camera. That sort of dark cone that's coming out of it, and those spikes. Those are effects from the camera and the lenses. And different cameras will give you different effects, but the color, that's the actual color of the star, and it is coming from the surface, of course. It's super fun.
Yeah, those spikes are from the support veins on the secondary mirror. So anyway, it's 550 light years distance, so take a look at that. Now, on the top right there, you can see a cluster of stars. That's a globular cluster known as NGC 6144. Which is located, which is actually at a distance of 29,000 light years. Incredible distance. And especially when you can even see the stars there. That means those stars are very bright even from that distance. All right, so I just wanted to also mention this star is of course Chris's favorite star. So go out and indeed. Yes, indeed. So,
and Anthony says it was a 5-minute exposure. He typed that into the chat on YouTube.
Oh, cool.
And I should say that globular star cluster is actually a great one for people to look for. There's another one right in the neighborhood too called M4. Both of them are easy to find in the sky because they're right next to a bright star. So just a little insider's suggestion for those of you with scopes.
That's great. So yes, definitely take a look at Antares. It will be climbing higher and higher in the sky in the next few months. All right, so there are some other stars to look for. 3 of them are in the northeastern portion of the sky. They are Vega, Deneb, and Altair, and 3 of them form an asteroid known as the Summer Triangle. And when they're visible in the evening at this time, of course, we know that summer is upon us. And in fact, the summer solstice occurs on the 20th at 8:32 p.m. PDT. And this is when the sun moves to its most northern point in its path around the sky, and is at noontime, local noon here in Los Angeles. The sun is at altitude of 79 degrees above due south. The day marks the beginning of summer in the northern hemisphere and the beginning of winter in the southern hemisphere. Turning to our morning sky, the 2 giant gas planets in our solar system, Jupiter, which is the brightest of the 2, and the second planet, which is Saturn, are visible. The moon is below Saturn on the 27th. And if you missed that, you can go out about the same time in the early morning, about 4 a.m., and see that the moon is between the 2 planets. And the next morning, it will be just to the left of the planet Jupiter. So here are our moon phases for this month. We've already had last quarter on the 2nd, and click here, there we go. And then on the 10th, we have new moon. On the 17th is first quarter, and then finally a full moon on the 21st, which is the strawberry moon.
Well, thank you, Patrick. Strawberry moon. We can all look forward to that and have some delicious strawberries grown right here in California. So, Katie, I think it's time for some pretty pictures of Katie along with some space weather. So, take it away, Katie.
Thank you. So we're starting with some 3D images. So if you have your 3D glasses, you can put them on. If you don't, that's okay, because we also have the non-3D versions. So here we have Ingenuity helicopter in flight. And if you have your glasses, here we go to the 3D version. And then this is a video of the flight of Ingenuity in 3D. You can see it on the bottom left there.
I need to find my 3D glasses.
I know, I'm jealous. I'm hoping people will comment in the chat and tell us how cool this is, because I know that must look really cool.
And here we have the Western Rim and Ejecta crater on Mars. We'll go to the 3D.
You might need to boost your volume a little, Katie.
How about now? Is that better?
That's better.
There we
Yeah,
go.
thank you.
All right. And here is the same crater, just zoomed in a little bit. And in 3D. And finally, for 3D images, we have some fun shots. And you can guess what these.
Who took this one?
I think it was the Nimoy family, maybe. We can hope.
Yeah. And now on to some beautiful, pretty pictures. These are taken by telescope demonstrator Anthony Perkic. This is Cassiopeia on the upper left there, and Galaxy Andromeda right in the middle. Beautiful image of the Milky Way and a telescope from Anthony Perkic. This is M20, the Trifid Nebula. And M8, the Lagoon Nebula. And this is beautiful Arcturus.
And was that last one also by Anthony, by the way?
Yeah, those were all Anthony Perkic images.
I recognized the pattern in his.
I was
his,
thinking the same thought. Yeah.
Yeah.
Yeah, beautiful. And then here we have some beautiful sprites or transient luminous events. So sprites are large-scale electric discharges that happen in high cumulonimbus clouds or thunderstorm clouds. And they occur at about 50 to 90 kilometers high, and they shoot up toward space. And they usually occur by discharges of positive lightning between underlying thunderclouds and the ground. And they're difficult to capture via camera because of the weak light that's emitted from them. So here's another beautiful image of the sprites. This is over the Czech Republic, and these sprites were detected by ESA, the European Space Agency's SWARM satellite, which measures and observes the Earth's magnetic field. So it's super rare to see sprites, and then it's even more rare to capture them from space, and that's what SWARM did, as well as being observed from the ground. So because of these observations, they can help scientists understand how sprites propagate into space. And here is the SWARM constellation over Earth. And SWARM can only measure sprites if the lightning is strong enough and the energy produced by transient luminous events, such as sprites, could charge more than 800 electric vehicles, where one single bolt of lightning could only charge 20. So they are very strong. Ending here with a beautiful image of sprites and the Perseids over the Czech Republic. And all of this is just to say that these findings with swarm observations and ground observations could improve scientific models of the ionized part of the Earth's atmosphere, which is also known as the ionosphere.
Wow.
Yeah.
What are those dots? The dotted lines following the celestial sphere?
Yes,
Off
looks
the
like
right?
star trails.
They do. Oh, okay, maybe they're just a little pixelated on my screen.
I want to say that sprites are very difficult to capture because they last for a fraction of a second. So you really have to catch them at the right moment.
I've never seen one.
Same. So on to some space weather. This is an image of our sun from today, and you can see there are two sunspots currently on the sun, AR 2829 in the lower left and 2827 in the upper right. And sunset spots are also associated with coronal mass ejections, which help determine the aurora forecast for Earth. So here we have the sun on the left and the current coronal mass ejections from today on the right. So you can see it is pretty quiet for today. And this is from NOAA. So they make this aurora forecast from that information. And on the bottom left is the probability color. So you can see most of it is that bright green, which is a lower probability of seeing aurora today. But you can go to the NOAA website for space weather and the aurora forecast daily to see these updates.
Thank you, Katie. Fantastic. Very, very interesting. So no auroras from LA normally, and unfortunately none even if you're up in the north. Now, there's a story that's very, very interesting. I'm going to go quickly because we're slightly behind tonight, but not too badly. But comets are very, very interesting. Now, the way they work is far from the sun, they're icy, they get close to the sun, the ice is sublime, they sublimate, they form a gas, that gas surrounds the comet, forms an ion tail and a dust tail. But there are also metals on comets, things like iron, potassium, nickel. They're actually there. And if the comet gets hot enough, close enough to the sun, those metals can vaporize and they can actually join the coma, that gaseous cloud around the core, the nucleus. And we see that. You can see some of these spikes in here are labeled. The red ones are labeled as iron, the others, the blue ones are nickel, and the nickel, it's actually glowing. It needs to be a gas in order to do that. Now, the crazy thing is when some of these comets travel far from the sun, researchers that studied one recently, and I'm forgetting the name of the comet, of course, at this part of the show. It cooled down. They still saw gaseous iron and nickel. Why was it there? We're a little bit confused. We don't understand why there's still gaseous iron and nickel. It should re-solidify. It shouldn't hang out, and it's there in numbers that looks like it still needs to be reproduced. Not only that, maybe you remember that interstellar comet, Borisov. It flew in from another solar system, went through ours, heated up enough that it gave off a tail, gave a little bit of a coma. They saw heavy metals in Borisov, an interstellar comet. So things are a little crazy. It seems like comets are, well, heavy metal comets. And you know what that means. That's right.
Disrespect your surroundings.
So, of course, I don't know if it said to disrespect your surroundings. It's been playing games on us a little bit there, but that's an old clip. All you longtime All Space Considered fans probably saw that clip, I don't know, 3-4 years ago, the last time we had a heavy metal. I think it was Heavy Metal Planet at the time. So anyway, a lot of good fun there with the heavy metal comet. So very quickly, an update on Ingenuity and update on Perseverance briefly. The Ingenuity helicopter did complete its first one-way trip. It flew off on its 5th flight, landed at a new location, and there it is. Hello, Ingenuity. So landed safely, was waiting off in the distance for Perseverance to go find it. Sure enough, Perseverance did find it, although it's a shot from the air here of it flying. Another shot, this is flight 6 now. Notice the ground's kind of shaking back and forth a little bit there. That doesn't look too stable. And indeed, it had a problem. The problem ended up being the way that the times were recorded on some of the images it was using to stabilize. They were off, and it got into sort of this, I don't know, an increased, an unstable thing, but they got out of it, they landed safely, they think they fixed it. So we need to see if they did indeed fix the helicopter, but ran into a little bit of a problem. And there's the little helicopter off in the distance. Now, Perseverance itself has been taking some images. This is Watson, the camera that's designed to zoom in and see perhaps signs of life. Well, it's working pretty darn well.
Oh, yeah.
The mast cam is working pretty well as well. Now, if you've got those 3D glasses, get them handy again. We've got one more 3D image for you. Here's just some rocks, what they look under in Mars light. Here they are under more Earth light. It looks kind of like you'd expect out in the desert somewhere. And finally, in 3D light. So if you've got those blue or cyan and red 3D glasses, put them on, you can feel like you're on Mars. Now, of course, Perseverance got a companion on Mars. The Chinese successfully landed their rover, and that rover is not small. It's about the same size as Curiosity. You can see it there. There's this shot here. It's really, really big. They just put on really, really big solar panels. So instead of sending a nuclear power source like we did with Curiosity and Perseverance, they just put huge solar panels on it. But it's rolling around now. There are pictures. You can check them out. So now we are thrilled to move along to our final segment tonight. We're thrilled to have Dr. Paul Byrne join us and talk about Venus. Paul, are you there? There you are. Welcome.
Hi, everybody.
Welcome.
Can you
Hi.
hear me okay?
Absolutely. You sound great.
Awesome.
So we're excited by some Venus announcements, and I'm going to give a very brief rundown here about what we know about Venus, what we've been doing. So first of all, Venus, it's that bright planet in the sky. It's in the evening sky. It's in the morning sky. It's known as the morning star. Sometimes it's not a star. It's a planet. That's the moon, of course, near it, the crescent moon. When you look at Venus through a telescope, it actually goes through phases. It can be a crescent. It can be a gibbous. Yes, it has to be on the other side of the sun to be a full Venus, and that's kind of hard to observe it there. But notice, it's really cloudy. You don't see the surface easily. It's basically the same size as Earth, very, very close to it, but it evolved differently. It's only about, it's 70% of the distance we are from the sun. So not that much closer to the sun, and yet it's hot enough to melt lead on the surface of it. Even with all those thick clouds, you might think clouds, it's blocking sunlight. No, other way around, like climate change, it's holding in the heat. Earth has a moon, Venus doesn't. Very, very sad about it. And that might have something to do with why the way we are and the way Venus is, but we need observations to find that out. Mariner 10 flew by, took some pictures of Venus. This is in the ultraviolet. Again, we're not seeing the surface there. So NASA designed the Magellan spacecraft. We're skipping a bunch of missions to Venus, by the way. I'm just skipping right over them. But Magellan was a super interesting mission. It had radar mapping built in. So when it got to Venus, it was actually able to see things like volcanic peaks, which are interesting. Those are not glowing red due to lava. That's just colored for height. Here's a color of sort of the continents, or a map of the continents of Venus. Indeed, it seems to have sort of structures that look a lot like our continents, but were they formed in the same way? We just don't know. Very little information is there about them. The Europeans sent the Venus Express mission there, and indeed, it saw signs that there were temperature changes happening on the surface that might have been consistent with active volcanism today. Wouldn't be super surprising, but I don't know if I believe it completely. It seems compelling, but I want more data. More data are always better. Volcanoes on the surface, can we see those? Is that something to believe? I don't know. Well, why are we even talking about this? I think it was 2-3 days ago now, new NASA administrator made the announcement that they'd chosen which are the missions that are going to be the next big flagship missions, and 2 were chosen to go to Venus. Veritas was one, and the other is called Da Vinci Plus. So, Paul, why are you excited about this? Dr. Byrne, you study planetary planets. You look at Earth analogs, I know. You look at places on Earth that are sort of like places out in the planets to figure out what happened, and you want to compare Earth to there. But, you know, why are you so excited about this? What is this going to mean for our exploration of Venus? And, you know, why should we care?
Okay, well, so here's why we should care. So thanks, David, and it's a pleasure being here with all of you, and I've really enjoyed the show so far. It's all underpinned by a single question, and like you said, Venus orbits about 3/4 as far from the sun as we do. It's about the same size, and it's made of about the same stuff in about the same proportions. It goes around the same star, and it's the same age as Earth. So how is it that you can have another large rocky world just next door that for all the world is our sibling planet, but it's not our twin? That is the crux of the question for Venus. However you want to phrase the specific science objectives and questions we have about its climate and about its interior, how do you end up with a planet that looks so weird and different compared to Earth? And there's a couple of reasons why this matters. So I'll talk about this in a minute. We have 2 leading models for how Venus got the way it did. And we don't know right now which of those 2 models is correct. But the reason this has taken on, this has always been interesting. And since we discovered back in 1962 with the first successful interplanetary flyby by the Barnard 2 spacecraft, which up until that point, up until certainly in the 50s, people were writing science fiction stories set on Venus, where this was a lush, tropical, rainforest-like world, because the assumption was it was that little bit closer to the sun, and therefore it was just a little bit warmer. And then Barnard 2 in 62 put pay to that. It was like, no, using radio waves, it was able to determine that the surface, or the lower atmosphere of that planet, is scaldingly hot. And David, you described it as being hot enough to melt lead. I have to confess, I have absolutely no intuition for the temperature required to melt lead at all. So when I talk about it, I say it's the same temperature as a self-cleaning oven, because I know that when my self-cleaning oven is on, I don't go near that thing. That is the kind of prevailing regular temperature at Venus. The point is that
there is a crazy man that has hacked his oven that he can bake in it on the self-cleaning cycle because he wants to make Neapolitan pizzas. So,
you know what? I mean, and to be fair, that would be quite an effective way of doing that. You would get that for free on the surface of Venus. Of course, you'd have no capacity to eat the thing because you would be dying. But the point anyway is that we've known for 50 years that Venus is a world right next door and is quite unlike our own. But the reason this has taken on a particularly special, I guess, significance in the last, let's say, 10 years or so is we're now getting into looking at these extrasolar planets, these exoplanets, right? And right now, in terms of our capability with our modern telescope technologies, we cannot resolve the difference in size between an Earth-sized world and a Venus-sized world in orbit of another star. So anytime you hear a press release or you read a press release about, oh, an Earth-sized world found somewhere, you may as well replace it with Venus-sized world. It means the same thing. Yeah. And when someone says Earth-like, they're lying, because we have no definitive evidence that an Earth-sized world is necessarily Earth-like. In fact, it could be Venus-like. Mm-hmm. And if we don't understand why Venus ended up the way it did, or let me put it this way, why Earth has ended up the way it is,
Yeah, we may
We are
be able
not
to-
going to have a framework or context for making sense of what we see around other stars. Right? So that's why this matters. This matters for a bunch of reasons, but that's the most important one, I think. If we're serious about looking for life on other worlds, looking for habitable conditions and understanding what planetary habitability means, we're not going to find it on asteroids. I personally, and I would happily come back for another talk about why I think the ocean worlds in the outer solar system are sterile. We're not going to find it in these small worlds. Mars, we think, may have been habitable for a long time, but it was never habitable the way Earth was. It simply was too small. We have one of these two models for Venus says that it may have had liquid water oceans for 3 billion years. So we need to understand if trees and squirrels and beaches or a self-cleaning oven is the outcome we can expect for large rocky worlds. And we don't know. And the way we're going to answer that question is we're going to go back to Venus.
Well, now, why do you think these missions are going to tell us about that? What capabilities are they going to bring to this problem?
All right, so I want to kind of just presage my answer by saying this. No 1 or 2 or 5 missions is going to solve Venus. That's just not going to be how it works. That's not how it's worked for Earth. We know from 25 years of sustained Mars exploration that we still don't really understand Mars all that well. We still have major questions to answer. So these missions are not going to kind of, put Venus in a box and we can move on. But they are going to help us take 2 major advances forward in understanding Venus. But I will also say this. I promise you, in 10 years, when we're starting to kind of work through the consequences of what these missions have told us, we will have whole new questions that we don't have the imagination to ask yet. So it's going to get worse. Our understanding of Venus will in a way get worse when we start getting a better understanding of it, but that's how it always goes in science. Okay, so let's take Veritas first, which is the image I think we have up right now. Veritas is a radar mapper. So you've mentioned that the reason Venus is so bright in our sky, its albedo is about 0.7, right? So it reflects about 70% of the sunlight it receives. That's because it has this global layer of H2SO4 clouds, of sulfuric acid clouds. So that's one of the many ways in which Venus will try to kill you if you go near it. And the point about these clouds, it's this cloud layer, like you said a minute ago, David, that's retained that heat. That's basically, it's both a consequence of and a retainer of what we call the runaway greenhouse effect on Venus. That's why it's so hot. Venus, the surface temperature is the highest of any of the rocky worlds, and so it's like the hottest surface in the solar system, hotter than Mercury, because Mercury is only heated by solar radiation. It doesn't have an atmosphere, it doesn't have a climate, and it's the climate that's doing it to Venus. And the reason that matters is because you cannot, therefore, look at a planet and look at its distance from its parent star and just assume you can measure it, you can estimate its temperature. That we now know that doesn't work. So what basically the way we try and see, the way we are going to see the surface, the way we have in the past seen the surface of Venus, is we have to use radar. Radar can penetrate through that thick cloud layer, just like we've used radar to see through Titan's thick hazy layers, Titan's Saturn's biggest moon. So we've had radar measurements. The United States sent the Magellan mission. In fact, the Soviets, Vega 15 and 16 missions also carried radar, although they weren't as capable. So we know kind of to first order, right? Top of the line, we kind of know what the surface looks like. The problem is that the resolution of those data are very limited. They are comparable to perhaps what we had for Mars after the Viking missions in the 70s. That was enough for Mars to give us a sense of what the overall story is, but we missed an awful lot of details, right? We missed a lot of details. There's a lot of fine stuff you cannot see with that kind of resolution. And when we went back in the 2000s with much higher resolution, much more capable cameras on Mars, we came to learn a new world. That is what Veritas is going to do. We have some key questions right now we cannot answer with the currently available data. We are only going to be able to actually test our hypotheses and refine our ideas by getting back there with much higher resolution data. And you're showing here some of the SAR resolution. So SAR is synthetic aperture radar. It's the type of radar that Magellan carried, 150 to 280 meters. The kind of global mosaics were downsampled to 75 meters per pixel. They really weren't actually that high, and that's still pretty coarse, because it takes about 3 or 4 pixels for anything to kind of come into form. So you're not seeing objects 75 meters across, you're seeing objects maybe 250 meters across. You're seeing maybe a football field, or maybe several football fields. That's like the smallest thing you can see. So again, you're going to see where all the big things are, but you're going to miss an awful lot of detail. Whereas Veritas is going to have the ability in places to take resolution images as sharp as 15 meters per pixel. When we had that resolution at Mars, suddenly that began to just show this whole new world for us. So again, I do not have the imagination to predict what we are going to find, but it is going to allow us to understand that surface and its history way better than we do now, right? And one of the things we're going to look at is, what is the history of how the surface came to be the way it is? One of the most strange and surprising things that Magellan told us back in the early 1990s is that there's fewer than 1,000 impact craters on Venus. And that is weird, because look at the moon through a telescope. Right? It's pretty easy. You get to 1,000 pretty fast. There are no craters smaller than 3 kilometers in diameter on Venus, because the atmosphere eats up things that would make craters smaller than that. But there are no gigantic craters on Venus either. There are no basins like Oriental or Imbrium or Tranquillitatis or Calorus and Rembrandt, or what the hell else is out there? Hellas, Argyll, or Utopia. It's like, you just don't have those giant basins on Venus. Now, surely Venus had them. The moon has them. Mercury, Mars, right? Earth had them. On Earth, they're gone because of plate tectonics. Now, we don't know why they're gone on Venus. We do know they're gone, which means that less than 1 billion years of history, well, actually, that's a big unknown as well, but we think less than 1 billion years of history is preserved from the surface of Venus. That's not much of a record as planets go. Veritas is going to be able to help us tell not just what's there topographically, but also from this image here, Veritas is going to carry for the first time a capable spectrometer that is going to be able to actually tell us the spectral characteristics of the rock. It turns out that when I said you can't see the surface from space, I kind of lied. There's a few windows around 1 micron or so in the infrared that you can see through the atmosphere, and you can there's a lot of issues. You get scattering in the atmosphere, so the resolution's poor. But for the first time, Veritas is going to actually try and tell us something about what the rocks are made of. It won't definitively say it's this rock and it's that rock type, but it will be able to tell us where the differences are. And then on the basis of lab measurements we already have and will continue to get, we can start making educated guesses about not just what the rocks are, but how they change in space. And because Veritas is going to give us really powerful control in the 3D, in the third dimension, us geologists rely on that to get timing. Right? Stuff that's sitting on top of other stuff. So in 10 years, when Veritas flies and starts returning these data, we are going to learn of a new world. And a lot of our existing models for Venus will be proven to be wrong. We'll develop new ones, and we will realize just how complex, and I suspect, by the way, dynamic. So David, you were saying a minute ago about volcanism. I am absolutely positive there are volcanoes erupting right this second on Venus. In fact, I would eat my desk, preferably if it's made of chocolate, if we find there are no active volcanoes. And there's a few reasons for that. And the fundamental one is this: how is it you can have a world about 85% the mass of Earth and not have it be volcanic? Earth is erupting all the time. And I don't mean the eruptions like on Iceland. I mean the seafloor spreading volcanoes, right? The vast majority of volcanic activity takes on the ocean floors. There's no way that's not happening on Venus. There are tens of thousands of volcanoes. There are probably millions of discrete volcanoes on Venus. We just can't see all of them. And we have a global layer of H2 of SO4, right? This is sulfuric acid. H2SO4 is made of H2O and SO2, 2 of the 3 dominant things that comes out of a volcano. The cloud is not chemically stable over billion-year timescales, which means it's either new or it's being replenished. And the only way I can think of doing that is volcanoes. We know there are some very, very young, geologically young flows, because we know that from the radar data. They've got very fresh edges. There's no way that thing isn't erupting right now. And there's no way it's not tectonically active right now either. It doesn't mean plate tectonics, but it means stuff is moving. Yeah. Veritas is going to be able to tell us that.
Okay. Now, I remember way, way, way back from, gosh, even undergraduate. So this is decades ago. There were folks talking about how Venus might resurface itself globally every so often. Is that still
no, that's wrong.
Idea?
That's wrong.
That always seemed a little false to me.
Yeah.
I thought it should be more like Earth with plate tectonics in a continuous process versus something that's sort of like, we're all lava now and now we're all solid.
Yeah, so there were some bad ideas that were developed back in the day. And the problem is that there wasn't very much a way of new data to kind of test them, right? Yeah, the reason that global resurface is, let me be very clear for folks who are watching, right? So we do know that there's a weird dearth of craters. And we do know that the average surface age, on which we estimate from cratering records, right? So this is a whole other conversation, but The way we get ages from craters is it's assumption based upon assumption based upon assumption, for, sleight of hand and a bunch of it is a precise but inexact science. So if someone tells you something to more than two significant figures, they're lying in terms of age, unless and until we get there and sample stuff. But the surface of Venus on average is younger than 1 billion years. But the thing is, we don't quite know if the bell curve of ages is like a really tight one where they're all clustered around that age, which is what the global resurfacing model will have you believe. Or if in fact the bell curve might look a bit like this, and there are some parts of the surface that are really young and some parts that are really, really old. And I mean billions of years old, but we don't know. However, if you look at different areas, unless you assume spatially disparate places that look sort of the same are in fact the same layer, which we never do on Earth, you cannot find support for that global vomiting of lava. I mean, that's what I learned as a kid, right? That this thing every 750 million years has vomited itself out. And that is consistent with the observations, basically, but it's geologically wrong. This thing is probably just, in fact, this is very hard to measure because the data we have at Magellan don't really help us test this. It's probably likely that the rate of volcanic eruption is about the same as Earth proportionately. And it's coming out, like you said, in sort of splotches. Veritas, through repeated imaging, is going to be able to, with the resolution it's going to be able to get, will allow us over, we know what the modern impact flux at Mars is, because we can take images with Mars Reconnaissance Orbiter and see new craters form. And we miss a few, sure, but we can spot them. And you can go to Google and image, the same land, 6 years apart as a new crater in it. We won't probably see new craters at Venus because, like I said, you don't get a crater smaller than 3 kilometers, and the things to make things that 3 kilometers and above are pretty rare. But we might see a change in a lava flow or a new lava flow. That's the kind of thing that goes straight onto the cover of Nature or Science, because it would be the kind of smoking gun we don't yet have to understand whether there's active volcanism on Venus, which of course there is, but we don't know for sure. So that's one of the ways. So Veritas is going to tell us what modern Venus looks like and going to help us look back in time by seeing what's preserved from the surface. Then you get to Da Vinci Plus. And Da Vinci Plus is a different thing. And one of the most exciting aspects of the announcement 2 days ago is that we're going to get 2 missions, but they do 2 different things that are all part of the same kind of story, which is understanding present Venus and understanding its past. Now, Da Vinci Plus, the star of the show, it has an orbiter as well. So Veritas is a fairly capable big orbiter. Da Vinci Plus is a smaller orbiter, but the star of the show is this big meter-wide sphere of metal. And it's going to be dropped down through the Venus atmosphere. And you can see this image here. This is what we call the entry, descent, and landing phase, or the EDL sequence. Now, the EDL sequence for Mars probes, particularly for Curiosity and Perseverance, features this just bananas sky crane, SWAT team helicopter maneuver, right? This photograph is a little misleading because what you can't really see is, you'll notice the second last thing from the bottom, it's the little ball, is the little sphere is still on its parachute. The way you actually get to the surface, now the probe is designed to operate during its fall, during its transit through the atmosphere. It's not a lander. It's not designed to survive the landing. It's not expected to. It probably will, because these things tend to be extraordinarily well engineered, but it's not, there's no plan for it to operate on the surface. So if you get a picture of the surface of this thing, it'll be lying on its side and it'll be bonus, right? And it'll die 20 minutes later because the surface is self-cleaning oven. But unlike what this photo suggests, this thing is not coming down on a parachute all the way down, because if it did, it would overheat too fast. One of the keys for operating anything with modern technology is that it cannot spend that long going through the atmosphere or it overheats. So the way you get to the surface is you come in on your heat shield, and then you blow the heat shield away, you get rid of it, you come on, you got your back shell, your drogue chute comes out, then you'll pull that away from whatever else is the structure around you, then the main chute comes out. But when you get to an altitude of 60 kilometers, you drop your chute, you just cut it off and you free fall. Because getting to the surface of Venus is much more like getting to the surface of the ocean floor than it is anything else. So this thing's going to free fall ballistically for 60 kilometers. It'll take about an hour, about a kilometer a minute, as this thing just gets hotter and hotter and hotter. On the way down, it's going to do 2 important things. It's going to take, at regular intervals, it's going to ingest a little bit of the atmosphere, and it's going to measure the composition of the atmosphere with onboard sensors. And those sensors are going to measure specific compositional things, particularly the abundances of noble gases. And I'm going to skip over the detail of why, except to tell you this. Measuring what the composition and abundance and ratios of different noble gas isotopes will tell you extremely precisely what basically the history of volcanic degassing and even how much water Venus is born with. And those two, I referred earlier to the fact that there's sort of two models for Venus. One is that Venus was always ruined. It started off with that runaway greenhouse effect from what we call the magma ocean phase. It was just too close to the sun. It was never able to cool down. It was never able to condense any steam in its atmosphere to oceans. It was just wrecked from the beginning. That's model one. Model two is that it's possible, and really exciting work in the last 13 months has started to kind of add a new dimension to this discussion. It may be that if you are able to protect yourself with a hemispherical cloud, you might actually be able to get out of that early tumultuous phase. You might have enough ability to reflect light that you can prevent the runaway greenhouse effect being triggered from that early time when you're really hot. And once, if you get out of that phase, which Earth did, then there's no reason you can't condense the steam in your atmosphere, develop oceans, have a nice, well, we don't know the composition of the atmosphere, there's processes that play into that, but that's the scenario that gets you to the point where maybe Venus is habitable. And we know, for reasons I'm going to skip, that Venus had a lot of water in its past. We don't know if that water was steam, which is model one, or if it was liquid water, which is model two. Veritas, or rather Da Vinci, as it goes down and is sampling the atmosphere and measuring those noble gases, the aim is to be able to tell, simply from the measurements, it will take over 60 minutes. That's all. It's going to be able to put a pin in which of those two models is correct. It won't answer everything, but it will tell us which model is the right one, or probably some weird third thing we haven't thought of yet. But the point is, that's what Da Vinci Plus is going to do. Now, there's more cool thing that's going to do. As it's falling, remember, it's not designed to operate on the surface, but it is going to get there. It's like, you know, anytime a plane takes off, that plane is coming down again, whether it's going to be controlled. No. Same with this probe. This probe is not going to go back up again. It's going to hit the ground. They've targeted it onto a type of terrain that we call tesserae. Tesserae is not a geological term. It's a term that Russian scientists invented in the 80s to describe these really, really weird looking, mucked up terrain that just, it's really tectonically deformed, it's folded, it's crunched, it just looks really weird. It occupies about 8% of the surface of the planet. We don't know what the tesserae are. If someone says we do, they're lying. We don't even know that all the different parts of the planet where Tessera is exposed is the same kind of rock, because the word is simply a way of describing the morphology of this material. There's no independent evidence that it's the same rock everywhere or it's the same age everywhere. Like, legitimately, when you people ask people, well, what's the most interesting thing about Venus, or from a geological perspective, where would you most likely to go? They'll tell you tesserae. Now, we've never tried, and by we I mean human beings, there's only been about 6 or 7 successful landers ever on the surface of Venus because of how difficult it is to get there and operate there. They were the Soviet Venera landers and then the Vega landers in the 70s and 80s. Those landers touched down on the relatively smooth expanses, which occupy about 80% of the surface of Venus, which we know are basaltic lavas. No one's ever tried to land on the Tessera because we don't know. We do know that they're really rough from radar data. We don't actually know what they look like, because of course radar data are not the same as looking at, you know, Google radar images and then Google the same area in Google Earth or maps, and it doesn't look quite the same. So we don't know what the tesserae look like, and we certainly don't know what they look like at the scale of a lander. So we don't know how to build a lander that will be resilient to a tessera, because what you really want to avoid is spending a lot of money on a thing and then it kind of lands and then tips over and then the radio antenna is pointing to the ground, and then your mission is just not going to work. Da Vinci Plus is going to take nested photographs for the last few kilometers. As it's coming down, as the haze starts to clear, this ground that it's going to be meeting is going to start swimming into existence. And it's going to be taking these photographs at ever higher resolutions. And those photographs are going to, A, provide unprecedented information on the geology of this weird kind of rock, or at least this particular exposure of it, and is going to provide critical data that we'll be able to use for engineering purposes to later in the future, in the next decade, develop a lander that would safely land on the Tessera.
Well, super interesting. I had a question, and we have a question from our YouTube chat as well. Is there any chance that the Da Vinci probe could hit a portion of Venus's atmosphere that would just be unlucky, a little bit like the Galileo probe did on Jupiter, where they think they just hit a dry region?
Right.
Could that happen, or is this global enough we're not worried?
So, okay, to be fair, it's probably not a problem. We don't actually know definitively quite what the dynamics are in the Venus atmosphere. We have some hints from the Japanese, the JAXA Akatsuki probe, which is currently operating and has been there for 5 years in orbit of Venus. It uses infrared and UV cameras to see through different layers in the atmosphere. We get a sense of what the vertical mixing, what the horizontal dynamics are. But it's at a much larger scale than what a probe would experience, right? So it's not the same as, say, flying. You can look at a hurricane from orbit, but you want to get the hurricane hunters in there to actually get that high resolution data. Our current thinking of the Venus atmosphere is that somehow below about 110 kilometers or so, that's a layer or a point we think is the homopause. And below that, we think that the atmosphere is totally mixed. And we don't know that for sure, but it's likely. And so the view is, for our purposes, because of the vagaries of the Venus atmosphere and because of how slow how slow the planet rotates versus the atmosphere is actually super rotating, it was much faster, but it's still not that fast, that we think there's a good chance that you're going to get a representative profile, no matter where Da Vinci Plus's probe goes in. Now, that is not to say, like I said a little while ago, despite how exciting these missions are, this is, in my view, it should be seen as the start of a new era of Venus exploration. These two missions are not going to kind of resolve every question we have. What is interesting is we actually don't know what the atmosphere, what the middle atmosphere is like. We do know that the only other place in the solar system that's functionally like Earth, that is Earth-like, is the Venus atmosphere. Between 60 and 55 kilometers, the temperature and pressure are basically room temperature. You'll asphyxiate quickly because it's all 96.5% CO2. Right. But if you had a mass scuba gear on or something like a firefighter wears, you could potentially stand on the gondola of a big aerial platform. In fact, there are concepts to do this where humans could wear shirt sleeves and operate safely out there. So you could operate a balloon, an aerial platform of some kind, using a lighter than air ship, and operate up there potentially for months. The Russians flew with their Vega missions in 1985, 2 balloons, Vega 1 and 2, a few days apart, that were provided by the French. And those balloons operated for about 44 hours and traversed about half of the circumference of Venus. Now, the reason they only lasted 44 hours, they actually lasted longer, but because the Vega mission was just this, basically the Soviets were like, we're going to go to visit Hades' comet, but we're going to go and use a gravity assist Venus. Why don't we just carry some stuff to Venus? That's what they did. So they dropped these balloons and they dropped landers. But then the probes, which were on their way to the comets, went out of range, and so we lost tracking with the balloon. That's why they only operated for 44 hours. They didn't last very much longer. In fact, that's the same deal with the landers. That the longest landed operation, I don't remember which Venera it was 127 minutes. It probably lasted longer than that, but that's how long it had to see its orbiter before it moved out of range. There, modern technology, modern batteries, modern solar charging capabilities, modern Mylar and Teflon balloon materials, you could have a balloon up there for 6 months. The longest stratospheric balloon on Earth operated in comparable conditions for 2 years. So you could be up there for a while. And if you did that, which I think you should, you would build on the Da Vinci Plus measurements by characterizing, are there variations in time? If you're up there for much longer than 60 minutes, you can take much more precision, right? Because you can take as many samples as you want. You might be able to measure a wider range of things. This is not to say Da Vinci Plus is not going to be critical. It is. But I want to try and shape people's expectations. It's like how we've been doing Mars. Right? We build up. Each mission advances on the other, raises new questions and offers further opportunities to answer old ones. So what would be amazing is we get Veritas to give us that new topography and image data, which we badly need. We get Da Vinci Plus to give us compositional data of the atmosphere in the atmosphere, because you really won't get it without being in the atmosphere, and images of the tesserae. And then later you send more spacecraft. You characterize the rate at which the atmosphere is being lost. You characterize what the dynamics and the chemistry of the atmosphere writ large is by being in the atmosphere. You land on the plains and you sample with modern analytical capabilities what the rocks are made of. That would immediately tell you, in the course of 8 hours, you would learn 4 billion years of history. You land then in the tessera because Da Vinci Plus and Veritas have given you improved data for how you design something to safely land in the tessera. You eventually then look to try and get a sample of the atmosphere that you bring back to Earth for labs and analysis on Earth. And then eventually, maybe in the 2060s, I don't know, you look to try and bring some of the Venusian crust home, like we're beginning to do from Mars. This is how we do it. We do it in steps. It's going to be hard. It's going to be expensive, but they are not reasons not to do it. Right. But the way we get there is we build up decades worth of experience plural decades to understand how to do it. Because I cannot emphasize this enough. If we are serious about understanding how our own planet came to be and how it stayed habitable for 4.5 billion years and why it isn't ruined, we need to understand the history of Venus. That's the only way we are going to be able to understand our own world, both its past and its potential future, to say nothing of large exoplanets. It all hinges on Venus.
Yeah, well, and also Earth is undergoing dramatic climate change right now, and we're understanding that through Earth observing missions. But to have something understanding Venus and have that point of data, to have that datum there, it's crucial in my opinion. It is the more we know, the more we can understand what's happening on our own planet. Now, one question from our audience out there. Very technical question about the different bands that are used, and the question was, why was the X band chosen for the radaring system? Because the thought was it doesn't go through clouds very well. My thought was that would be Earth clouds the X band doesn't get through, that it penetrates Venus clouds just fine.
That's right.
And the other bands wouldn't be so good, the ones that are on Earth satellites.
So the short answer is I don't know, because I'm not on the team and I'm not privy to whatever decision making went into that. I can tell you that Magellan was an S-band radar. There is currently one thing we haven't talked about at all yet, and I know we could talk for hours, because if you start me, I will continue talking until you cut the Zoom off. Right now, there is another potential Venus mission in the works. Across the pond, the European Space Agency is about on probably Wednesday. This coming Wednesday, we're expecting to hear the outcome of a multi-year effort to characterize and select their M5 mission. So whereas NASA has Discovery, New Frontiers, and Flagship are sort of the three levels of increasing cost in planetary missions, the European Space Agency doesn't break things out by planetary and astro and helio. They lump everything together, but they have S, M, and L missions, small, medium, and large. And their medium class missions are comparable to New Frontiers, which is NASA's 850 million kind of thing, a little bit less than that for ESA. Their M5 call, I don't know how many they started with, but they ended up shortlisting. Often how these things work is you might get 20. Like in the case of Da Vinci Plus and Veritas, there were about 20 missions put in. In February of last year, that was narrowed down to 4. Those 4 teams were given about $1.5 million each to really fully refine their project proposals. And then we had the selections on Wednesday. I don't know how many there were at the beginning. 3 missions were shortlisted about 3 years ago for a longer, what we call a pre-phase A. Last year, one of those 3 missions was taken out of contention. It was deemed to be too expensive, wouldn't be able to make that cost cap. And the 2 remaining missions, like I said, ESA doesn't break things up by planetary and astro. One is a deep space telescope looking at high Z values way back when, called Theseus. And the other mission is called Envision, and it is a Venus radar mission. And we are going to hear on Wednesday which of those 2 will get picked. Now, you might ask, well, we already have Veritas as a radar mission, and why would we want to send Envision? Well, that's never stopped us sending Mars Reconnaissance Orbiter, Mars Odyssey, Viking, Mars Express, Mars Orbiter mission. How many missions at Mars have cameras? If you go to a planet, you bring a camera, regardless of what your overarching science objectives are. If you go to Venus or Titan, you have to bring a radar. Envision would carry an S-band radar. It has a different science focus and a different purpose than Veritas. There's huge complementarity, but not the same thing. So it's like I'm going to bring an infrared camera on this mission. I'm going to bring a visible camera on that mission. The X-band radar has a particular function. It's got a particular capability. It has particular power and mass requirements that allow Veritas to be competitive within the Discovery cost box, which is about $500 million, which objectively is a lot of money, but in space exploration isn't really for ultimately a 20-year mission. So the idea is X-band was chosen to be the best thing for Veritas. If Envision flies, it will probably carry an S-band radar. And one of the reasons why that's exciting is because that's the same kind of radar Magellan had, which means you could directly do apples to apples. You could downsample the resolution of your Envision data and do a direct comparison to look for change between Magellan and Envision, right? Wow. And of course, there are other synergies I can't even think of to having 3 missions operating around the same time around this one planet. So. Yeah.
I completely agree with you. There's no reason not to have multiple missions. Complementary instrumentation can be sent. These missions aren't built in a vacuum, and they're not built right now. These were the proposals to build the spacecraft, and there's always tweaking that's done along the way. So exactly. If the Europeans approve their mission, scientists in Europe, scientists here, will talk and say, wow, if you do this to yours, we can do this to ours, and then even more science is done.
That's exactly it. Exactly it. Yep.
So
And we're
it's very-
hoping to see that. We're hoping to see this Venus ecosystem develop now, where these
Yeah.
teams are communicating.
It's exceedingly exciting times. Venus has been ignored more than 30 years now. It's time to go back, and we are. And what year do these missions launch? Provided all goes well, of course.
All goes well. I'll need to go and check this for sure. It's something of order 2028, 2029, and if the vision is selected, it goes in 2031.
Yeah, I thought it was something like that too. Oh, my cat's getting on my mouse here, trying to mute my own audio. That would be bad. Well, thank you so much for joining us tonight. Wonderful speaking with you. Like I said, once we're back in person, and folks, that's going to happen sooner than you might think. We'll make announcements as we know more about when we can reopen. Again, foundation members, feel free to join our foundation, and you'll get invited to come see Griffith Observatory in person on June 18th. That's right, we're going to have a member event before we reopen to the rest of the public. You can come in, see the Samuel Ocean Planetarium, the Leonard Nimoy Event Horizon Theater, see all our wonderful exhibits and all our halls, see what we've done to some of those exhibits to update them, and just enjoy the observatory, take a look through a telescope. And thank you so much for joining us tonight. Thank you, Paul, Dr. Paul Byrne, again, from North Carolina State University, a real expert in planetary science, and we're going to keep you on our list of people to talk about as these discoveries are made. So
you bet. We've got a lot more Venus to talk about.
Yeah, absolutely. And thank you so much. Yeah. And again, folks, this presentation tonight was made possible by Griffith Observatory, which is run and operated by the City of Los Angeles and the Department of Recreation and Parks. And much of our presentations are made possible by the Griffith Observatory Foundation and their generosity that helps us buy equipment and everything else we do to make all this possible. So thank you, members, for everything you do for us. And thank you all for joining us tonight. And we'll see you next month.
Good night.
Good night, everybody.